Good evening and welcome back. Tonight, we're going to step back more than 200 million years to follow one of the most extraordinary stories in the history of life, the rise and fall of the dinosaurs. How did these animals go from small, two-legged reptiles to the giants that ruled the land, sea, and sky? What kinds of worlds did they live in? And how did they adapt as continents shifted and climates changed? And finally, what led to their sudden disappearance after more than 160 million years of dominance? We'll trace their story from the Triassic, through the Jurassic, to the end of the Cretaceous, and then look at how their legacy lives on today. It is a tale of evolution, survival, and sudden catastrophe, written across ancient rocks and fossils. As always, I'd love to know where in the world are you listening from and what time is it for you, whether you're drifting towards sleep or simply curious about the distant past. I'm glad you're here. Now, let's begin. About 252 million years ago, life on Earth came closer to complete collapse than at any other time in history. The event is known today as the Permian-Triassic extinction, though paleontologists sometimes call it simply the Great Dying, because no other phrase captures how devastating it was. Imagine a world where 9 out of every 10 living things, whether in the seas or on land, simply vanished. Coral reefs disappeared, whole forests crumbled, and the oceans became graveyards. If we had a time machine to witness it, we would step out into landscapes so barren that they might look more like the surface of Mars than Earth. Scientists have pieced together the cause with remarkable detective work. The evidence points to colossal volcanic eruptions in what is now Siberia, known as the Siberian Traps. Over the course of hundreds of thousands of years, these eruptions belched unimaginable volumes of lava and poisonous gases into the atmosphere. Carbon dioxide levels soared, creating a greenhouse effect so extreme that ocean waters warmed, lost their oxygen, and turned hostile to most marine life. Sulfur dioxide brought acid rain, devastating the land plants that still remained. The world entered a vicious cycle of warming, dying, and more warming. By the end, around 90% of all marine species and roughly 70% of terrestrial species were gone. When the dust and firestorms eventually subsided, the survivors faced an emptied world. In some places, only ferns grew, which paleontologists know because of fern spikes in the fossil record. Layers of rock where spores of ferns are suddenly dominant, as if these hardy plants rushed in to cover the ruins of forests. On land, most of the great reptilian lineages of the Permian had been swept away. Among the few that managed to cling on were small, pig-sized herbivores called Lystrosaurus. Fossils of this squat, tusked creature have been found from Russia to Antarctica, showing that it spread almost everywhere in the early Triassic, likely because there was so little else around to compete with it. The planet itself looked very different from what we know today. All the continents were still fused together into the supercontinent Pangaea, an immense landmass that stretched from pole to pole. The interior of Pangaea was an unforgiving desert, with oceans so far away, the land baked under intense heat, and seasonal rains often failed to reach inland regions. Imagine a single continent that contained both the size of Africa and Asia combined, with vast stretches of arid plains where only the toughest creatures could survive. The edges, along the coasts, were more forgiving, but even there life was sparse compared to what had come before. In this unpromising setting, new groups began to take tentative steps into prominence. Among them were the archosaurs, a broad family of reptiles that included the ancestors of crocodiles and, importantly, dinosaurs. The archosaurs had features that gave them an advantage in a harsh world: more upright postures for efficient movement, stronger lungs, and possibly higher metabolisms than many of their competitors. While early archosaurs were not particularly large or numerous at first, their adaptations allowed them to endure the Triassic climate and steadily spread. The early Triassic, then, was a peculiar time. It was not yet the age of dinosaurs, and it hardly looked like an age of anything. Life was recovering in fits and starts, with ecosystems so fragile that a drought or a flood might wipe out an entire region's population. Yet, slowly, small reptiles, amphibians, and plants began to rebuild the tapestry of life. Rivers cut through the deserts of Pangaea, providing strips of green where animals could gather. Insects, always opportunists, diversified and thrived. Strange amphibians the size of crocodiles lurked in swamps. And amidst this scattered cast, the archosaurs were quietly taking hold, ready to set in motion the next great chapter in Earth's history. The stage was set, though no one could have guessed it then. Out of this world of scarcity and hardship, a lineage would emerge that would eventually give us Diplodocus and Triceratops, Velociraptor and Tyrannosaurus rex. But at this early moment, they were only modest creatures surviving in a battered world that had only just avoided complete lifelessness. If you had walked through a Triassic forest about 235 million years ago, you would not have recognized the Earth as the planet we know. The sun was hotter, the atmosphere had more carbon dioxide, and the very smell of the air would have been strange to us. Oxygen levels were lower than today, and the ground was often baked hard by seasonal droughts. The land was still dominated by Pangaea, the single supercontinent that sprawled across nearly a third of the planet's surface. To the east lay vast deserts with dunes larger than skyscrapers. To the west ran stretches of swampy floodplains, and scattered in between were forests of conifers and cycads that struggled through searing summers and sudden storms. It was here, in this demanding world, that the first dinosaurs quietly stepped onto the stage. The earliest dinosaurs were not mighty giants. In fact, they were so modest that for years paleontologists overlooked their remains, confusing them with bones of other reptiles. The clearest evidence comes from the Ishigualasto Basin in modern Argentina, known as the Valley of the Moon. The rocks here preserve one of the best windows into the late Triassic world. Fossils show a community bustling with reptiles, amphibians, and early mammals. Among them were the very first true dinosaurs. Herrerasaurus, discovered in the 1960 seconds, was one of these pioneers. It was roughly the size of a large dog, weighing perhaps 300 kilograms, and walked on two legs. Its teeth and claws reveal it was a hunter, likely feeding on small reptiles and amphibians. It was agile rather than imposing, built for speed rather than brute strength. Alongside it lived Eoraptor, another early dinosaur, slender and light, probably an omnivore that scavenged for insects, small prey, and plants. At just a meter long, it was hardly the stuff of nightmares, yet it represents one of the oldest known branches of the dinosaur family tree. Other early dinosaurs appear in scattered sites across the globe. In southern Africa, footprints preserved in ancient mud show small bipedal animals darting across floodplains. In what is now India, faint traces of Triassic dinosaurs hint at their early spread. Fossils from Tanzania reveal a creature named Nyasasaurus, which some researchers argue may be even older than the Argentine specimens, dating to about 243 million years ago. If that interpretation holds, it would push the origin of dinosaurs back another 10 million years, placing their birth surprisingly soon after the Great Dying. What is clear is that dinosaurs began as a minor group, a handful of species in a world where other reptiles still reigned supreme. To understand why dinosaurs remained in the background for so long, one has to look at their competition. The Triassic was filled with fearsome creatures. Giant amphibians lurked in rivers, some as long as cars, snapping up fish and the occasional small reptile. On land, the real heavyweights were the Rauisuchians, huge crocodile-like predators that could grow 7 meters long and stalk the plains with terrifying jaws. These were the apex hunters of their day, and compared to them, the early dinosaurs looked like nimble but insignificant upstarts. Even in the herbivore ranks, dinosaurs did not dominate. Early plant eaters included hefty, barrel-bodied reptiles like placerias, which weighed nearly a ton and grazed in herds along river valleys. Next to such robust animals, the small, bipedal dinosaurs were unlikely candidates for future dominance. And yet, they had something special. Their skeletons showed traits that gave them an edge. Their legs were positioned directly under their bodies, allowing them to move more efficiently than the sprawling gait of most reptiles. This upright stance made them quicker and able to sustain longer bursts of activity. Their hips and ankle joints hint at agility, while their lungs may have been more efficient than those of their contemporaries, perhaps similar in design to the highly effective respiratory systems seen in modern birds. These subtle advantages were not enough to make them rulers overnight, but they helped them persist in ecosystems where others faltered. For millions of years, dinosaurs remained a footnote. They shared the Triassic world with mammal-like reptiles, giant amphibians, and the dominating crocodile kin. They lived in the shadow of more imposing predators, scavenged what they could, and grew slowly in number. If you had been able to survey Earth's animals at 220 million years ago, you might have dismissed dinosaurs as a minor group unlikely to last. No one then could have guessed that these small creatures, tucked away on the margins of ecosystems, would one day give rise to the largest land animals the world has ever seen. Their story was only just beginning, and the twist of fate that would propel them forward was still a few million years away. The rise of dinosaurs did not begin with a glorious charge. It began because the world fell apart again. About 201 million years ago, at the boundary between the Triassic and the Jurassic, Earth lurched through another crisis that erased much of the competition and cleared space on the stage. Paleontologists know this event as the end Triassic mass extinction. It was not on the same scale as the Great Dying at the end of the Permian, but it was devastating all the same. Something like 3/4 of species vanished from the record. In the seas, many shelled creatures that had limped through earlier troubles finally failed. On land, large reptiles that had dominated for tens of millions of years lost their hold. The winners would be the survivors nimble enough to endure the chaos and fortunate enough to inherit the empty niches that followed. The culprit lies in stone across 3 continents. When Pangaea began to split, the crust tore open along a growing seam that would one day become the Atlantic Ocean. From these deep cracks poured floods of basaltic lava in volumes that are difficult to imagine. Geologists call this vast outpouring the Central Atlantic Magmatic Province. You can stand on its frozen remains today in Morocco, in the Fundy Bay region of Nova Scotia, across New Jersey and the Hudson Valley, and in parts of Brazil. These are stair-steps of black rock stacked hundreds of meters thick, the cooled record of a planet bleeding molten stone. The eruptions did not last a weekend. Evidence suggests a series of pulses over several 100,000 years. Each pulse would have delivered great burps of carbon dioxide and other gases to the air. The carbon shows up as sharp swings in the isotope record preserved in limestones and lake sediments. The rocks speak a simple truth. The atmosphere changed fast, and life struggled to keep up. The climate response would have been severe. Carbon dioxide warms the planet. Sulfur gases can seed clouds and bring acid rain. Short-term cooling can follow an eruption while aerosols hang in the air, only to be replaced by longer-term warming as greenhouse gases take over. Oceans absorb much of this burden. Warmer surface waters hold less oxygen. As mixing slows and chemistry shifts, oxygen starves deeper layers, and the water becomes hostile to many creatures that once lived there. In some marine sections that cross the Triassic and Jurassic boundary, tiny fossils of plankton fall off a cliff in abundance. Reef builders falter. Ammonoids, those elegant coiled mollusks that had been a symbol of resilience, crash and then reappear as a few hardy forms. The message is consistent. Food webs were knocked down and rebuilt in simpler forms. On land, the victims were not random. The Triassic had been the age of many impressive reptiles that were not dinosaurs at all. There were the Rauisuchians, deep-chested hunters with crocodile faces and long legs that stalked floodplains like living siege engines. There were the Phytosaurs, crocodile-like predators with long snouts and nostrils set near their eyes that haunted rivers and lakes across Pangaea. There were armored etosaurs that trundled through fern prairies, bodies covered in bony plates, snouts for rooting through soils. These groups had kept the early dinosaurs in the minor leagues. Across boundary rocks on several continents, these once common animals either vanish or dwindle to rare holdovers that do not last. The plant record shows its own turmoil. Pollen and spore assemblages change abruptly in cores from ancient rift lakes of eastern North America. It looks like forests were periodically burned and replaced by pioneers. After the fire comes the fern. Then slower growing trees edge back in, only for another pulse to shake them. If this sounds like conjecture, visit the ancient rift basins that bracket the First Atlantic. The Newark Supergroup, which is the name for a chain of lake and river deposits from Nova Scotia to the Carolinas, preserves a diary of the crisis written on page after page of mudstone. The sediments are banded by climate rhythms that match the wobble of Earth's orbit, a metronome known as Milankovitch pacing. Between these fine bands, you find layers rich in charcoal from wildfires, abrupt shifts in pollen, and above them thick sills and flows of basalt from the magmatic province. It is a neat sandwich. Stable lakes, then ash and floods of lava, then sudden ecological turnover. You can trace the same story in the High Atlas of Morocco, where dinosaur footprints begin to appear above thick flows of basalt, as if new tenants arrived once the paving cooled. Not everything perished. The crocodile line did not vanish. Small, more lightly built crocodilomorphs crept through the wreckage and endured. Turtles made it through. The small, nocturnal mammal relatives kept their place in the shadows. And of course, the dinosaurs survived. Here is the important point. The earliest dinosaurs had been a minority in a world run by other reptiles. The end Triassic crisis removed many of those incumbents. It did not make the dinosaurs superior in an instant. It made the world friendlier to whatever could move fast, breed well, and take advantage of the new plant communities that spread across the recovering landscape. There are hints that dinosaur success was already gathering speed before the final pulse of eruptions, but the boundary marks a turning point that is impossible to ignore. In South America, assemblages above the line contain more species of true dinosaurs and fewer of the once common crocodile kin. In Europe and North Africa, trackways show herds of medium-sized two-legged animals crossing mudflats where once there were scattered small forms. In the American Southwest, in places like the Chinle and Kayenta formations, the change through time is a slide from mixed reptile communities to ones where dinosaurs are central characters. In broad terms, the extinction acted like a reset button. It simplified food webs. It opened ground-level plant niches and mid-level predator slots. It turned a world of rivals into a world of opportunities. Geography played a quiet role in this story. Pangaea did not shatter overnight, but the rifting that fed the eruptions also began to carve the supercontinent into northern and southern halves. Seawater started to flood into the new lowlands, cutting climate pathways and creating coasts where none had been. With new shorelines came moisture, and over time, greener belts that threaded between drier interiors. Where the Triassic world had been dominated by long arid distances and harsh seasonal swings, the early Jurassic saw more varied habitats. A creature with an upright stance, efficient lungs, and a flexible diet could travel farther, graze different plant communities, and pursue new prey. The small Triassic dinosaurs were built exactly that way. They did not need to reinvent themselves to take advantage. They simply needed room. When we think about mass extinctions, it is tempting to dwell on the horror. That is fair, but the history of life is also a record of rebounds. Ferns rush in after fire because they can. Lake plankton return because any patch of sunlit water invites their kind. Animals that are mobile and adaptable do well in the early stages of recovery. In a Triassic world that had been reset by flood basalts and climate shock, dinosaurs fit the template. They could run. Many were light on their feet and social enough to exploit openings quickly. Their respiratory systems likely allowed higher activity than many competitors. In simple terms, they were ready for a planet that had changed its rules. By the time the last lava cooled and the atmosphere drifted back toward a new normal, dinosaurs had moved from the margins to the middle of the story. The extinction had not crowned them kings, but it handed them the keys to empty rooms across two great landmasses. From that moment, the arc bends toward the familiar Jurassic world of long-necked browsers and confident predators. The takeover did not happen in a single season. It took millions of years and many local dramas we will never know, but in the broad sweep, the end Triassic crisis was the pivot. It created a world where dinosaurs could finally flourish. Once the smoke of the end Triassic upheaval thinned, the world was left with landscapes both wounded and strangely full of promise. For the animals that endured, the new Jurassic dawn was a world of open ecological space. Whole categories of predators and grazers had been erased. What remained were patches of opportunity, waiting to be filled. Into these gaps stepped the dinosaurs, creatures that until then had lived in the background, unremarkable compared to the hulking Rauisuchians and crocodile kin that had once strutted across Pangaea. With those rivals gone, the stage was suddenly much quieter. Dinosaurs, with their efficient lungs, upright limbs, and adaptable diets, began to expand into niches that had been unavailable to them before. Across the scattered continents of the early Jurassic, their footprints tell the story. Literally, in many cases. In the Connecticut River Valley of New England, in the highlands of southern Africa, and in the sandstone beds of western China, paleontologists have traced trackways where herds of bipedal dinosaurs once crossed riverbanks. These prints show animals of different sizes moving together, sometimes adults with juveniles alongside. The message is clear. Dinosaurs were no longer only scattered individuals. They were multiplying and moving in groups, spreading across the globe as the Jurassic began. The animals themselves began to branch into recognizable families. The plant eaters took one path. Their necks lengthened, their torsos deepened, and they grew more massive to handle bulk diets of ferns and conifers. These were the early sauropodomorphs, distant kin of the giants that would one day dominate the Jurassic and Cretaceous. A genus called Plateosaurus, found in Europe, already reached lengths of 7 to 10 meters by the late Triassic and early Jurassic. It was one of the first large herbivorous dinosaurs, with long neck vertebrae and sturdy limbs that allowed it to browse at different heights. Fossil bone beds in Germany have yielded dozens of individuals, suggesting they lived in groups and perhaps fell victim to droughts or floods together. Plateosaurus shows that even before the great sauropods like Diplodocus and Brachiosaurus, the evolutionary trend toward bulk and reach was already underway. The carnivorous branch of the family tree was no less ambitious. Small hunters like Coelophysis of North America, lean and lightweight at around 3 meters long, were among the earliest to flourish. Thousands of bones of Coelophysis have been found in Ghost Ranch, New Mexico, suggesting they were common and perhaps social, moving in packs or congregating in numbers. Their teeth were finely serrated, perfect for slicing into small reptiles and early mammals. Other early theropods, such as Dilophosaurus, recognizable by the twin crests on its head, patrolled floodplains of what is now Arizona around 190 million years ago. At over 6 meters long, Dilophosaurus represents a step toward the larger predators that would follow. It was not yet the apex hunter of its time, but it shows that carnivorous dinosaurs were already experimenting with size, strength, and ecological roles. Geography continued to shape their spread. Though Pangaea still held together, cracks were widening. Oceans began to seep into rift valleys, splitting the land into northern and southern blocks known as Laurasia and Gondwana. For the dinosaurs, this division was less a barrier than a canvas. With climates moistening in some areas and plant life expanding, herds of early sauropods pushed outward. Their remains have been found on nearly every continent, from South Africa to China to the American Southwest, evidence that dinosaurs had already become a global presence. It is striking how quickly they became central to ecosystems. Where Rauisuchians had once ruled as the top predators, theropods took over. Where armadillosaurs had once lumbered as the main plant eaters, sauropodomorphs spread. Within a geologically brief window, the balance of life shifted. Dinosaurs were not just surviving in the Jurassic. They were flourishing, diversifying into forms that could graze, hunt, defend themselves, and travel long distances. Their physiology seemed tailor-made for a world that had been cleared by catastrophe and was now rebuilding. The fossil record of this time gives us glimpses of a world in motion. In the red rocks of the Navajo sandstone in Utah, footprints of theropods march across dunes, showing they could cross arid deserts where food and water were scarce. In the forests of what is now China's Yunnan province, skeletons of Lufengosaurus lie in ancient sediments, showing that sauropodomorphs were already experimenting with larger bodies and longer necks. In the Karoo Basin of South Africa, bone beds hold a mix of early mammals and dinosaurs, testimony to an ecosystem that had stabilized with dinosaurs now at its core. The truth is that nothing inevitable guaranteed dinosaurs would take over. They were simply fortunate survivors with the right tools at the right time. But once given the chance, they proved remarkably capable of expanding into every available role. By the Middle Jurassic, they would be the undisputed masters of the land, a transformation so complete that we forget how close they came to remaining minor players. The Triassic extinction was their doorway, and they walked through it into history. When the Triassic faded into the Jurassic about 201 million years ago, the Earth was in the midst of a makeover. The supercontinent of Pangaea, which had stood unbroken for tens of millions of years, began to pull itself apart. In slow motion, what would become the Atlantic Ocean yawned open, widening centimeter by centimeter each year. This reshaping of continents also meant a reshaping of climates. Where the Triassic had been defined by vast arid interiors and long seasonal droughts, the Jurassic introduced a more generous environment. Rain fell more often. Seas crept inland. Lush river valleys and wide forests spread where desert had once stretched for endless kilometers. The vegetation itself changed dramatically. Conifers rose high in dense stands, joined by tree ferns, cycads, and horsetails. These were not delicate woodlands, but heavy, almost primeval forests where humidity clung to every surface. On the forest floor, mosses carpeted the ground, while in the canopies, towering conifers reached heights comparable to modern redwoods. This new abundance of plant life made possible a new style of animal life. It allowed for creatures that could eat constantly and in great volumes, the sort of animals that would never have been able to survive in the harsher, drier Triassic world. The animals that took advantage were the sauropods. They were unlike anything that had come before, and nothing has matched them since. Imagine a creature longer than a school bus, neck reaching high into the canopy, sweeping side to side like a living crane. Their skeletons tell the story of evolutionary innovation. Vertebrae in the neck were riddled with air sacs to lighten the load, and their long tails acted as counterweights. Their feet bore columnar bones like great pillars, designed not for speed but for supporting tremendous weight. These animals were designed to do one thing better than any other: consume plants in bulk. Brachiosaurus browsed at treetop level in what is now North America. Diplodocus, with its whiptail and extraordinary length of up to 25 meters, grazed the middle canopy. In Africa, fossils of Giraffatitan reveal creatures with necks stretching to heights of 12 meters. By the Middle Jurassic, sauropods had spread across every continent, exploiting the greenery of the wetter world. Their success transformed ecosystems. Herds of sauropods moving together could strip whole groves of trees, leaving behind clearings that would soon regenerate with ferns and cycads. This constant disturbance acted as a form of natural landscaping, maintaining open areas for smaller animals and influencing plant cycles. They were ecosystem engineers, reshaping their environment simply by existing in large numbers. It is no coincidence that in the Morrison Formation of North America, one of the richest Jurassic fossil beds, the remains of sauropods are found in staggering abundance. These were not rare creatures. They were the common background of the landscape, as everyday then as deer are in woodlands today. Of course, where there are herds, there are predators. The rise of sauropods also demanded the rise of hunters capable of challenging them, and in the Jurassic, those hunters were ready. But before we turn to the teeth and claws of the predators, it is worth pausing on the fact that all of this, the lush forests, the giant herbivores, the planetary reshuffling, was not inevitable. It was the product of shifting continents, volcanic pulses, and slow but steady climate change. Earth created a canvas rich in greenery, and dinosaurs responded by becoming giants. The Jurassic was the first time life on land truly tilted toward the colossal, and the animals that walked the Earth then still hold the record books for size. The greener Jurassic world did not only feed giants, it also built the careers of hunters that learned to live beside them. If you walk through the fossil-rich beds of the American West, the first thing you notice is how often giant herbivores show up. The second thing you notice is the steady presence of their shadows. The shadows belonged to theropods, the two-legged predators that tracked herds and tested them for weakness. In the Morrison Formation of the western United States, a belt of river plains and flood basins that ran from New Mexico to Montana, the top hunter was Allosaurus. It was not the heaviest carnivore in Earth's history, but it had a set of arms worth studying: hands with 3 strong claws, a mouth lined with serrated blades, and a skull built to withstand violent thrashing. One skull from Utah carries healed fractures that look like the result of a bad encounter with a spiked tail. The bones tell us that Allosaurus survived its mistakes and went back to work. Evidence for their behavior comes from messy places. At Cleveland Lloyd Quarry in Utah, thousands of bones lie mixed together in what many researchers think was a predator trap. Mud or shallow water may have lured victims and then held them, while more animals came in to feed and became stuck as well. The result is a jumble with a striking number of Allosaurus bones, which hints at group feeding, or at least repeated visits by the same species. There are sauropod bones with bite marks that match the teeth of Allosaurus and Torvosaurus, a close rival in parts of the Jurassic West. Many skeletons show injuries that healed, including broken ribs and smashed toes. Life in the Jurassic was not a gentle affair, and the bones preserve a record of that simple fact. The menu was varied. Beyond the great plant eaters with long necks, there were plated dinosaurs like Stegosaurus that stood as walking challenges. Stegosaurus carried 2 rows of plates along its back and a tail with 4 stout spikes. The plates were full of blood vessels and may have helped with display or temperature control. The tail was not for show. There are sauropod bones with punctures that fit Stegosaurus spikes, and one Allosaurus pelvis with a deep hole that many think came from a stegosaur swing delivered with very poor grace but great effect. This was the chess of the Jurassic. Herds and hunters moved across floodplain mosaics. Predators tested flanks for the young or the lame, and defenders had weapons that could break bone. Jurassic predators were not a single story. In Portugal, sea level changes laid down coastal sands and dune fields that later hardened into rock. In those rocks, the Laringa Formation has produced large theropods such as Torvosaurus and Laringhanosaurus, along with nests and eggs that give a domestic side to the tale. In East Africa, at Tendaguru near the Tanzanian coast, German-led expeditions in the early 20th century uncovered an entire community of Jurassic life. There were sauropods like Giraffatitan, and alongside them stood a tall predator known as Elaphrosaurus, a lighter hunter that may have sprinted down smaller prey. In China, the Sichuan basins hold Sinraptor and Yangchuanosaurus, big-bodied carnivores that patrolled forests that were dense and wet for much of the year. In each region the cast varies, but the pattern repeats. Large theropods sit at the top, a range of mid-sized hunters fill the middle, and small, keen-eyed predators take advantage of carrion, eggs, and anything unwary. How did these animals bring down prey that could weigh as much as a truck or a small house? The answer is in anatomy and in patience. The jaws of Allosaurus did not crush like those of the Cretaceous tyrants that would come later. Instead, the skull worked almost like a hatchet. Neck muscles drove the head down, the serrated teeth opened deep gashes, and then the predator pulled back, letting blood loss and shock do the larger part of the work. This is supported by wear patterns and by the architecture of the skull, which could flex a little during impact. This method would have been most effective against flanks and tails. The predator did not need to fell a giant with a single move. It needed to wound and then follow until the landscape finished the job. Trackways add motion to this picture. In Colorado and Utah, long strings of 3-toed prints march across ancient mudflats. Some trackways follow the lines of sauropod herds and keep a respectful distance, as if the hunter walked the edge and watched for a mistake. Others show sudden bursts where strides lengthen and the toes dig deeper, the signature of a sprint over short ground. There are rare places where the prints of a hunter and a plant-eater converge and then break apart, a fossilized moment of approach and retreat. These are simple lines in stone, but they carry a sense that is hard to ignore. The land was busy. The animals knew each other well. Above this terrestrial drama, another story was taking shape. The first birds arrived in the late Jurassic, and they came from the same general stock as the small theropods. The best-known early bird is Archaeopteryx, found in the Solnhofen limestones of southern Germany. Those rocks were once quiet lagoons isolated by reefs, where very fine lime mud preserved astonishing detail. The slabs show the outline of feathers around a small body, with a long bony tail, teeth in the jaws, and claws on the fingers. Archaeopteryx is a mosaic. It is a bird in its feathers and in the shape of its wishbone, which anchors strong flight muscles. It is a dinosaur in its teeth, tail, and hand. The flight feathers are asymmetrical, which is a sign of true aerodynamic function, not simple insulation. One isolated feather from Solnhofen has even preserved microscopic structures that match melanosomes, the pigment bodies that give color in modern birds. The feather appears to have been dark, perhaps even black. It is a humble but human detail. We not only know that a small Jurassic creature had wings, we also have a hint about the shade of those wings. Archaeopteryx did not appear without prelude. In northeastern China, in rocks a little younger than the traditional Jurassic but close enough to belong to the same chapter, there are feathered dinosaurs that look like halfway points in many directions. Anchiornis, a small creature with long feathers on arms and legs, shows that feathers were widespread among close relatives of birds. Xiaotingia and Orornis add to the roster. Some had veined feathers for display or for gliding between trees. Others carried simple filament coats that would have kept heat in during cool mornings. Together they show that feathers were not a single invention turned to a single use. They were a toolkit. Warmth, display, maneuvering through branches, and finally real flight grew out of the same basic structure. The first birds had to learn to live in a world full of sharp teeth. That may be why their bones are hollow and light, and why their shoulder girdles are strong enough to take repeated beating from flapping flight. In the Solnhofen beds, Archaeopteryx shares space with small crocodilian forms, with fish, with dragonflies as big as your hand, and with long-tailed pterosaurs that had already mastered the air. The pterosaurs were not birds at all, but a separate group of flying reptiles that took to the sky earlier in the Triassic. By the Jurassic, they were confident flyers that skimmed lagoons or hunted insects over forest clearings. The fact that birds invented flight in a world where competent flyers already existed tells you something about the richness of the aerial realm. The sky had room for more than one solution. What did early flight look like in daily life? Imagine a humid island chain in what is now Bavaria. The sun is high but softened by haze. Shallow pools rimmed by reef walls lie calm and quiet. A small feathered animal scuttles from the forest edge onto the flats, snaps up a stranded insect, and then launches with a few fast wing beats, gliding to a low branch. It is not a soaring gull and not a hummingbird. It is a cautious jumper that can climb and flutter and escape a sudden rush from below. Over time, stronger chests and shorter tails will make birds better at all of this, but the first chapter is already clear. Feathers that began as insulation and signal flags became airfoils. Arms that once pushed a body up a log became wings. There is a temptation to draw a line between the ground and the canopy here, to say that giants ruled below while a new experiment took place above. The truth is more intertwined. Many small theropods on the ground were likely feathered and warm-blooded, with quick hearts and high oxygen needs. Evidence for air sacs inside bones hints at respiratory systems more like those of modern birds than like those of lizards. The jump from ground runner to flyer was not a single leap. It was a long series of small steps taken by cousins in many habitats. Predators and first birds were parts of one continuous family that tried different strategies in the changing Jurassic world. By the end of the Jurassic, the outlines of later ages were in place. Large theropods held the role of apex hunters on most continents. Plated and armored herbivores kept them honest. Herds of long necks shaped forests and river plains simply by eating them. In the trees and above them, small feathered animals had taken the first real steps toward the modern sky. None of the famous Cretaceous names have arrived yet. That is still to come, but the system that would carry them was already built. By the opening of the Cretaceous, the world had traded the old Pangaean arrangement for a globe in motion. The giant landmass that once tied north and south together had begun to unravel along broad seams that filled with young oceans. What would become the Atlantic widened a little more each million years. The northern continents that we call Laurasia drifted apart from the southern group known as Gondwana. South America tugged away from Africa and left a ribbon of newborn seafloor between them. India cast off from Madagascar and started a lonely voyage across the equator toward Asia. Australia hung back with Antarctica, still linked by a cool land bridge that would one day fail. None of this was hurried, yet the accumulated change was enormous. With new seas came new coastlines. With new coastlines came fresh winds and different rain. And with that, the surface of life began to reorganize. Climate followed the continents. The Cretaceous was a greenhouse chapter. Carbon dioxide sat high, the poles were free of ice, and sea level rose to flood the lowlands. In many places, shallow epicontinental seas stretched inland for hundreds of kilometers. These waters were warm and often clear, a quiet realm for shellfish, fish, and marine reptiles, and a path for storms that pushed moisture far into the continents. River systems lengthened and branched. Floodplains expanded. Places that had once been seasonally harsh grew more forgiving. Even at high latitudes, the world was surprisingly temperate. Fossil wood and pollen show that Antarctica supported cool rainforests during parts of the mid-Cretaceous. In the north, places in what is now Alaska and Siberia carried conifer forests that endured long polar nights, which tells us that some dinosaurs lived through months of winter darkness and low sunday. Warm oceans were not always kind. At intervals, the chemistry of the seas shifted and oxygen levels dipped, a phenomenon geologists call oceanic anoxic events. These episodes often lined up with spectacular bursts of undersea volcanism that poured out lava on plateaus of the Pacific and elsewhere. The world warmed. Nutrients flooded the water, plankton bloomed, and then great areas of the ocean turned sluggish and breathless at depth. Black shales laid down in those times are still mined for their carbon today. For life on land, the consequences were indirect, but real. A rich plankton base supports fish and ammonites that fill coastal waters, which in turn feed pterosaurs and birds, and occasional hungry dinosaurs wandering tidal flats. When that base stumbles, shorelines change, food webs wobble, and ecosystems on land feel a nudge. The new geography made highways and fences at the same time. As South America and Africa parted, animals on each side began to follow separate evolutionary paths. Similar splits unfolded as northern landmasses pulled away from one another. Europe became a quilt of islands fringed by reefs and lagoons. Asia held broad interior basins raked by monsoon rains. North America grew a long, shallow sea down its middle later in the period, a feature that would one day be called the Western Interior Seaway. This inland sea divided the continent into an eastern land and a western land, and turned river floodplains into long green crescents along its shores. With isolation came local character. Dinosaurs on each continental stage began to look distinctive, not because they broke the rules of their kind, but because each landscape offered its own mix of plants, predators, and climate. Plants tell the clearest story of change. Through the Jurassic, conifers, cycads, and ginkgos had been the backbone of forests. In the early Cretaceous, a quiet revolution began among the shrubs and small trees under their shade. New forms appeared that made flowers and enclosed their seeds in fruits. These were the first angiosperms. At first, they were not spectacular. Many were low shrubs along lakes and streams. Some carried simple blossoms that would not draw a second glance today. But they had an advantage. Flowers enlist insects as couriers. In exchange for nectar or pollen, beetles and flies and early wasp-like creatures ferried genetic material from plant to plant. That bargain speeds change. It also encourages specialization. In time, the partnership would ramify into orchids and figs and oaks, but the first steps were modest and very effective. Evidence for this botanical shift shows up in lake deposits from Spain to China and in slices of rock from the American West. Pollen grains with the telltale shapes of flowering plants begin to appear in mid-early Cretaceous layers. Leaves with smooth margins and branching veins, different from the stiff needles and scale leaves of conifers, become more common. Seeds wrapped in fleshy coats suggest that some plants had already begun to recruit birds and small mammals as unwitting gardeners. Insects changed with them. Fossils in amber record mouthparts adapted for sipping, and bodies dusted with pollen that still clings after 100 million years. Bees in the modern sense arrive later, but the cast of pollinators was already busy. The rise of flowers did not push the old guard off the stage. Conifers still towered over many landscapes. Tree ferns still filled damp gullies. Cycads still dotted open ground. The change was one of balance and texture. Under the conifer canopy, patches of flowering shrubs turned the understory into a richer pantry. Along riverbanks, angiosperms colonized disturbed soils quickly and locked them in place, changing how floodplains recovered after a storm. On drier hills, early flowering trees began to form stands that dropped nutritious leaves to the ground each season. Herbivores noticed that kind of improvement. Smaller plant eaters could graze more efficiently, while larger ones could move from patch to patch and find regrowth sooner. Over time, this would reshape mouths and bellies, but in the early Cretaceous, it was enough simply to have more food in more places. Rain patterns shifted with the continents. As the Atlantic widened, warm currents flowed along new coasts and sent moist air inland. Monsoon systems strengthened over Asia as the mass of the continent stewed in summer heat. The result was a planet with more belts of seasonal rain and fewer continental interiors that went bone dry for months on end. In the rock record, this shows up as thicker stacks of river muds and fewer sequences of wind-blown sand. It also shows up as growth rings in fossil wood that mark steady seasons rather than wild swings. Dinosaurs moved with these changes. Herds followed rivers that now ran longer each year. Nesting grounds expanded along stable shorelines. In places close to the poles, dinosaurs adapted to low winter light, which may have favored animals with good night vision and warm bodies. The early Cretaceous brought new shorelines to life. Barrier islands rimmed long, low seas. Behind them lay marshes, deltas, and quiet bays. These were nurseries for fish and for the great marine reptiles that cruised the margins, and they were larders for anything that could wade or fly. Pterosaurs hunted over these waters with long, narrow jaws lined with fine teeth. Early birds learned to snatch insects over the reeds and to rest in shrubs along the sand. Crocodilian relatives slid into brackish creeks. Dinosaurs that wandered down to the flats left footprints that hardened into stone. The lines of those prints tell us that herds crossed at low tide and that small predators traced the edges where crabs and worms lay hidden. Not all change came from the sea. Mountains rose where continents met. As Africa drifted north, the Tethys Ocean between Africa and Eurasia narrowed, and arc chains of volcanoes flared along its edges. When India later approached Asia near the close of the period, the collision would raise the Himalaya, but even before that time the approach of plates altered winds and rainfall across a sixth of the planet. Erosion fed rivers with new sediments. Those sediments built broad plains that meandered from highlands to the coasts. On these plains, soils matured into layered profiles rich in clays and iron, a signal of warm, wet climates that linger year after year. Such soils hold plant roots well. They also hold dinosaur footprints perfectly. If you could take a slow aerial tour of the Earth at this time, you would notice how stitched together it looks by water. New seaways curve between lands. Lakes fill rift valleys where the crust has stretched. Marshes and forests spread like quilts over long, low shelves. The animals we follow were made for this kind of world. Long-necked plant-eaters could walk for days and never run out of forage. Horned and beaked grazers would soon appear and take advantage of quick-growing herbs along streams. Predators could patrol corridors of green that ran for hundreds of kilometers. In the trees, where shade met breeze, small feathered animals tried new ways of living. The setting was more generous than the Triassic and more varied than the Jurassic that came before. Variety is opportunity in biology. There is a final feature of the early Cretaceous worth noting. Recovery from the end Triassic crisis was long finished, and life had turned inventive. Experiments multiplied. On land, this shows in the mix of plant communities. In the sea, it shows in reefs built by new kinds of corals and in great schools of swift fish. In the air, it shows in a growing range of wing shapes and beaks among early birds and pterosaurs. The planet itself invited that inventiveness by offering mild climates, broad coasts, and corridors for migration. When we talk about the Cretaceous as a long chapter, this is what we mean. It is a time when the backdrop keeps opening and life keeps finding new roles upon it. If you want a place where deep time feels close enough to touch, go to the lake beds of Liaoning in northeastern China. The early Cretaceous ash that fell there worked a kind of quiet magic. It settled over ponds and forests, buried fish and leaves, and small creatures where they lay, and preserved even the texture of skin and the delicate filaments of feathers. The result is a gallery of moments from about 125 million years ago. In these slabs you can see a feathery outline haloing a small hunter. You can see a tail with banded stripes. You can see impressions of veined flight feathers so crisp that each barb stands out like a comb. It is as if someone pressed a bird into wet plaster and then lifted it away, leaving the memory behind. The first surprise of Liaoning is not that birds are present. The surprise is how many dinosaurs that are not birds wear feathers of their own. There is a little predator called Sinosauropteryx, with a fuzzy coat of simple filaments, a kind of down that ran from head to tail. Along its tail, those filaments appear in alternating dark and light bands, a natural barcode that hints at color patterns for camouflage or display. There is Microraptor, no bigger than a crow, that carried long pennaceous feathers on both arms and legs. Spread out, those 4 feathered limbs give the animal the look of a flying kite. Aerodynamic tests on models suggest it could glide well and perhaps even manage short bursts of flapping. In the same beds lies Uteranus, a predator big enough to make you step back if you met it, with shaggy filamentous feathers along its neck and torso. That single find tipped over an old assumption that large carnivores must have been entirely scaly. Feathers, it turns out, were not a privilege of the small. Feathers in these animals did many jobs before they ever lifted a body into the air. Insulation is the most obvious, especially in regions that saw cool seasons and perhaps winter frost. Display is another, which you can tell from the fan-like arrangements on tails and arms and the way some feathers form crests or trains that would have caught the eye of any neighbor. There is also protection for eggs and hatchlings. A parent with a coat of feathers could brood a clutch and keep it warm and shaded. In Mongolia, Oviraptorid dinosaurs were found posed over their ring-shaped nests with arms spread in a circle. The posture looks like a living umbrella. Modern birds do the same thing on a windy afternoon. The line that leads to birds carries a set of skeletal refinements that read like notes toward a flight manual. The collarbones fuse to form the furcula, the wishbone that braces the chest for the shock of each wing beat. The breastbone enlarges and begins to carry a keel where flight muscles can anchor more securely. The wrists become more flexible so that the hand can fold the wing against the body. The tail shortens into a compact stump known as a pygostyle, which lets tail feathers fan out and steer without dragging a long bony counterweight through the air. The lungs thread into a system of air sacs that invade the bones, making them light and stiff, and helping the animal move a continuous stream of fresh air through the respiratory system. All of that adds up to an engine with both power and endurance. Liaoning gives us early experiments. Outside China, we find later steps that look closer to familiar birds. Confuciusornis appears in the same general time window as Microraptor and Sinosauropteryx, but it already has a true beak in place of teeth, along with a pair of trailing tail streamers in some individuals that may have been used for display. A little later in the Cretaceous, seagoing birds such as Hesperornis in North America lose the power of flight and become expert divers, with legs set far back on the body and teeth in the beak for grasping fish. Ichthyornis keeps strong wings and has a mouth that mixes a beak at the tip with small teeth behind, a snapshot of a transition in progress. If you line these creatures up by age and by anatomy, you see a steady tightening of the system. Tails get shorter, sternums get deeper, wings get better at both lift and control. Another important thread runs in parallel. Many small ground-running theropods that are not birds carry quills and veined feathers as well. Velociraptor, for example, has bumps on its forearm, known as quill knobs, which in living birds are the anchor points where flight feathers attach to the bone. That means this hunter wore substantial feathers on its arms, even though it could not fly. Other fossils from Siberia, including a plant-eater named Culindodromius, show filamentous coverings and even plate-like structures that look like early experiments in quills among dinosaurs outside the bird line. Put these finds together, and the simplest explanation is that the genetic toolkit for making feathers and feather-like structures was widespread. Feathers were a common resource that different branches adapted for warmth, display, brooding, gliding, and only later, full-powered flight. The chemistry of color leaves its own quiet signals in the rock. Under a microscope, some fossil feathers preserve microbodies that match the size and shape of melanosomes, the pigment packets that give color to living feathers. Arranged a certain way, these bodies produce blacks and browns, and in other arrays they produce iridescent sheen. Analyses of Microraptor and Anchiornis suggest dark plumage with a glossy finish, the sort of shine you see in a grackle or a crow on a bright day. These are not absolute proofs of palate, but they are strong clues that the Cretaceous sky held creatures that did not only fly well, they also looked good doing it. Behavior comes through in flashes. There are embryos preserved inside thin-shelled eggs, spines curled in the same posture used by modern chicks just before hatching. There are adult birds and close relatives found with gizzards full of small stones, which in living birds help grind up food. There are crop contents that show seeds and fruits being eaten, a sign that the new flowering plants had already found diners among the feathered set. There are perching feet with a reversed first toe, perfect for grasping branches. There are wing claws in some early birds that would have been useful for climbing through dense brush, a sort of four-limbed agility practice before the final commitment to life on the wing. It is worth remembering that pterosaurs were still overhead through all of this. They are not birds, and they solve the problem of flight differently, with a long fourth finger that supports a membrane wing and a body also laced with air sacs. In the early Cretaceous, they are diverse and graceful, from tiny insect hawkers to forms with wingspans wider than a room. That birds evolved and radiated in a sky, already busy, tells you how many ways there are to earn a living in the air. The two groups likely divided the space by prey size, by flight style, and by habitat, much as swifts and gulls and hawks share our skies now without much complaint. The ground did not stand still while the air filled. As feathers spread through small theropods, bodies changed to match. Arms lengthened relative to legs in some lines. Tails shortened. The wishbone and the arrangement of shoulder bones became more robust. These animals ran well, they jumped well, and they began to flap for reasons that had nothing to do with long-distance flight. Flapping can help in a scramble up a steep trunk. It can help during a controlled fall from a branch. It can steady a body that is pouncing. Over time, those little assists become stronger and more coordinated, until one day a youngster does not just fall with style, it truly flies. Nests tell a family story. In Mongolia, neat ring-shaped nests belong to oviraptorids, with eggs arranged like a wreath and an opening in the center for the parent. In Portugal and China, trackways around nesting grounds show repeated visits by adults. In the American West, delicate eggshell fragments occur near lake margins, mixed with plant debris that would have cushioned a brood. The recurring theme is attention to the next generation. Shells harden with layers of calcium. Some eggs show pigments that would have camouflaged them in leaf litter or on sandy bars. Parents brooded and guarded. Chicks probably grew quickly, as suggested by bone tissues filled with fast-growing fibers and by growth rings that show seasons of plenty and scarcity. Taken together, all of this makes the early Cretaceous feel like a hinge. The feathered dinosaurs of Liaoning are trying many forms and habits. True birds are adding the structural pieces that turn flapping into sustained flight. The air above rivers and lagoons is busier. The trees hold more nests. Flowers have opened a new market in nectar and fruit. And the customers have arrived with beaks and quick metabolisms. Even the larger predatory dinosaurs are not entirely outside this story, since their young may have been fluffy and their bodies may have carried patches of filament for warmth or display. There is a quiet irony in this. We often speak of the age of dinosaurs as if it belongs to ground-shaking giants alone. Yet, one of the most lasting inventions of that age is a body plan that weighs as much as your hand and runs on seed and wind. The dinosaurs did not only conquer the ground, they colonized the sky in feathers, and the line that did so is still very much with us. Every sparrow on a fence and every heron in a marsh is a living Cretaceous legacy. By the middle of the Cretaceous, the world had settled into a rhythm that favored abundance. Seas reached far inland, rivers threaded wide floodplains, and warm rains fed forests and fern prairies from the equator to high latitudes. Plants answered this invitation with vigor. Conifers still stood in tall ranks. Cycads dotted open ground, and flowering plants worked their quiet revolution along riverbanks and lake margins. Into this pantry walked the great plant eaters, and they did not come alone. They came in numbers, in herds that could turn a valley into a moving horizon of backs and tails. In the south, the champions were titanosaurs. Patagonia is their best stage. Here, the bones of Patagotitan and Argentinosaurus mark bodies that push the limits of what land can support. Imagine an animal as long as 2 city buses and as heavy as a small cargo plane, neck sweeping through treetops, while the hind feet churn the ground into soft ruts. These creatures were not rare accidents of evolution. Nesting grounds like Aucamahuevo in Argentina preserve thousands of eggs in repeated layers, a sign that titanosaurs return to the same broad sites season after season, much as sea turtles do today. Many eggs contain embryos with tiny teeth and even skin impressions. The shells are thin and porous, which suggests that parents covered the nests with vegetation so that compost heat incubated the clutch. Whole generations rose from such low mounds, then moved out across the plains in bands that browsed as they walked. Africa and India tell a similar story with local accents. In Egypt's Baharia oasis, where dunes and palms now hold the horizon, rocks record the presence of Paralititon, a coastal giant that grazed near mangrove-like swamps. On the Indian subcontinent, before it drifted north to meet Asia, the stocky Isosaurus browsed through floodplain forests and left behind limbs with strong muscle scars. On Madagascar, Rapatosaurus roamed an island world of rivers and seasonal drought, and the skeleton of a juvenile shows growth lines that reveal a fast pace of life in a challenging climate. Titanosaurs were not a single mold. Some carried armor plates embedded in the skin. Some had relatively long forelimbs that raised the chest as if built for high browsing. All shared a body plan that was a living bridge between ground and canopy. In the north, a different caste dominated. Hadrosaurs rose to become the most common large herbivores across many regions. They were the grazers and browsers of their day, and they came equipped with one of the best chewing machines in Earth's history. Their skulls held batteries of hundreds of teeth arranged in stacked files that slid against one another like careful gears. As one tooth wore down, another moved up to take its place. This allowed them to grind tough plant matter with steady efficiency. Bone beds in Alberta and Montana hold the remains of dozens of individuals packed together by floods, a strong hint that these animals moved in herds. Some hadrosaurs carried head crests that were not for armor, but for signal. Parasaurolophus wore a long tube that curved back over the neck. Reconstructions of the spaces inside suggest that air resonated through it like a musical instrument. A call might have rolled across a marsh for kilometers, a deep foghorn note that gathered the herd or warned of danger. Ceratopsians added a new look to the northern prairies. Early relatives began small in Asia, but by the late Cretaceous in North America, they had grown into stocky animals the size of a pickup truck, with skulls that were a mixed message of defense and display. Triceratops is the best-known example, with a heavy neck shield and 3 forward spikes. The neck frill anchored strong jaw muscles and also presented a billboard to other members of the herd. Behind the frill, a barrel of muscle moved a body on 4 solid legs. These animals could shear shrubs and small trees with a parrot-like beak, then chew with batteries of slicing teeth. In bone beds on the Great Plains, scattered clusters of juveniles appear near adults, which suggests social structure and perhaps family groups. In Mongolia's Gobi Desert, where dunes once marched, the smaller Protoceratops gathered in such numbers that whole slopes are littered with their skeletons. Some are found in pairs facing one another, frozen in postures that look like sparring. Herd life left marks in the landscape that you can still touch. Trackways run in parallel lines for hundreds of meters across beds of hardened mud. The spacing between footprints stays regular, as if the animals kept pace with one another. Sometimes a smaller trackway angles in and runs inside the line of a larger set, the likely path of a juvenile keeping close to a parent. Bone beds accumulate where rivers bend and drop their load. These collections tell us not only who lived there, but also who lived together. In Alberta's Dinosaur Park Formation, the remains of multiple ceratopsian species occur in the same layers, while in Montana's Two Medicine Formation, hadrosaur nest sites appear with a pattern of reuse, as if the herds returned each season to familiar ground. Skin and color rarely survive, but when they do, they offer a sudden jolt of life. Hadrosaur mummies from the western United States preserve pebbly scales and the outlines of the body, even down to the shape of the hands. Chemical studies of pigments in some feathered relatives of herbivores point to patterns of browns and reds, a sensible palette for a world of floodplains and forests. The overall impression is not of drab herds but of animals tuned to their surroundings, some with display patches for social signals, others colored to vanish when still. All this abundance did not mean safety. Predators were never far away, and the defenses we admire in these herbivores exist because teeth and claws were practiced and persistent. Horns are costly to grow. Armor is heavy to carry. Tail clubs make movement clumsy in tight forests. No animal invests in such equipment without good reason. The reason paced the edges of every herd and watched for a stumble. Predators are the punctuation in any ecosystem. They are the commas that slow the herd and the periods that end a chase. In the late Cretaceous, the punctuation marks were large and sharp. They came in different alphabets on different continents, but each set performed the same task. They tested the edges of herds, trimmed the slow and the careless, and kept the landscape honest. In western North America, the sovereign was Tyrannosaurus rex. This animal was not merely big, it was a moving argument for what bone and muscle can do when pushed to the limit. The skull alone could be as long as a person is tall. The jaws closed with a force that turned bone into splinters. Tooth crowns were thick and oval in cross-section, built like chisels rather than knives, which allowed the bite to punch through horn and ribs without snapping the blade. The teeth often carried deep wear and chips, a sign that hard targets were a daily reality and not a last resort. The neck muscles that powered this machine were anchored on a set of vertebrae, braced like a bridge. You could not miss a tyrannosaur in life, and you cannot miss it in the fossil record either. It leaves pathologies behind, broken ribs that healed, tooth abscesses that ate into the jaw and then closed over with new bone, bite marks on the faces of other tyrannosaurs that matched the pattern of their own teeth. It seems the rulers sometimes fought one another at close quarters. The tyrant family did not spring fully formed. Earlier in the Cretaceous, smaller and lighter relatives held the same role on northern continents. Gorgosaurus and Albertosaurus in Canada were slimmer and faster, with long shins and feet that suggest a hunter that could run down hadrosaurs in open country. In Asia, Tarbosaurus filled the top slot and hunted herds of duckbills and horned dinosaurs on broad basins that dried to dust in late-season winds. These animals show another pattern in their biology. The young and the adults did not live quite the same lives. Juveniles were more lightly built and could chase smaller prey, while adults moved into the heavy work of tackling armored or horned animals. This shift with age spreads pressure across prey communities and may be one reason the family dominated so completely in the north. Cross the Atlantic and head south, and you meet another dynasty. In South America, the giant role fell to the Carcharodontosaurids, the shark-toothed lizards in name and in spirit. Giganotosaurus was one of them. It was long, deep-chested, and built for wide strides, with a skull that carried long, serrated teeth shaped more like steak knives than chisels. Carcharodontosaurus in Africa shows the same plan. These animals likely hunted with slashing bites that opened long wounds and bled large prey into submission. Their fossils often occur with remains of the biggest plant-eaters of their time, which suggests a food web that paired big knives with big tables. The arms on these hunters were short but not useless. They were sturdy enough to clutch and steady a strike. Neck muscles were enormous. The whole front half of the animal reads as a delivery system for the mouth. In Africa, another story unfolded along river deltas and backwaters. Spinosaurus loomed there, a predator that broke the rules that seemed to hold elsewhere. It had a skull with the long, narrow shape of a fish-eater. The teeth were conical rather than serrated, a better tool for gripping slippery prey. The nostrils sat well back from the snout tip, which kept water out of the airways when the head was submerged. The tail was tall and flexible, a good fin for lateral sweeps. Leg bones were dense and heavy, which would have helped reduce buoyancy. Taken together, the features paint a picture of a hunter comfortable in water. It likely patrolled channels and reed beds and snapped at fish the size of a man. There are even coprolites that contain fish scales in abundance, which is strong if unglamorous support for the idea. Spinosaurus was no less a terror for being aquatic. It simply chose a different theater. Madagascar offers yet another accent. There, the abelosaurids took center stage. Majungasaurus was the local heavyweight, a thick-skulled predator with short bulldog arms and a face built to take a beating. Wear on its teeth and damage to bones hint at a style of attack that involved clamping and holding rather than swift slashes. Bite marks on bones of its own kind suggest face biting during dominance contests. The island setting likely favored a pugnacious generalist, and Majungasaurus looks the part. Across the water in India, Rajasaurus shows a similar profile with its own ornamented skull and stout body. These animals did not match the sheer size of the northern tyrants or the southern knife-bearers, but they were perfectly tuned to the seasonal rivers and patchy forests of their home ranges. Not every hunter was a colossus. The middle and small ranks were busy and inventive. Dromaeosaurids, the raptor family, brought speed and tactics to the hunt. They carried a sickle-shaped claw on each hind foot that could be lifted clear of the ground while running, and then driven into prey at the right moment. Skeletons show long arms with strong grasping hands, and many species preserve quill knobs along the forearm which are the anchor points for substantial wing feathers. Feathers on these animals were not for flight. They were likely for display, for warmth, and for balance and bracing during a grapple. Utahraptor in North America and Dakotaraptor in the same region later were large enough to trouble juvenile sauropods or lone hadrosaurs. Velociraptor in Mongolia was smaller, with a narrow snout and long, low skull. It hunted in a land of dunes and scrub, and probably favored quick strikes and careful retreats. There is a famous specimen that died locked with a protoceratops, each animal with a limb in the grip of the other, both buried when a dune collapsed. The scene looks like a fossil of a fight stopped mid-sentence. Troodontids and small tyrannosauroids filled the clever hunter niche. Their skulls had large orbits and expanded regions for the forebrain. The inner ear and balance system were well developed. These details suggest quick reflexes and good night vision. Some likely hunted at dawn and dusk along river margins. Oviraptorosaurs add an odd note to the chorus. Many were omnivores with deep beaks and strong jaws. Some crushed mollusks or cracked nuts. Others brooded open nests and guarded their eggs with outstretched arms. Their role in the predatory economy sat somewhere between thief and opportunist and dedicated hunter, a reminder that categories blur in the real world. How do we know what these animals ate and how they behaved? The answers are in marks and chemistry and the geometry of bone. Tooth scores and gouges on prey bones can be matched to the mouth that made them. Coprolites carry bone shards and muscle fiber that pass through the gut and tell you who was eating meat and how thoroughly it was digested. Stable isotopes in teeth preserve the chemical flavors of water and prey, which can separate river hunters from dry country runners and can even suggest seasonal movements. Growth rings inside bones show how fast a predator grew and whether it paused during lean times. Trackways measure stride and speed, and sometimes preserve a stumble or a change of direction when a chase went wrong. The record is a series of postcards, not a film, but there are enough cards to assemble a real itinerary. Predator communities were not simple pyramids with a single heavy animal at the peak. They were layered. In western North America, along the shores of the inland sea, You could find a tyrannosaur as the top hunter, a mid-sized dromaeosaur that ran the brushy corridors, and small troodontids that took rodents and hatchlings. In South America, a carcharodontosaur might claim the fattest herbivore, while a pack of noasaurs or small abelisaurids picked off the careless. In Asia, where deserts bordered seasonal rivers, you could watch a tarbosaurus slide through a stand of low trees, while flocks of small feathered hunters flushed lizards from under shrubs. Each level affected the level below, and each moved with the herds. It is tempting to draw simple rules for how these animals hunted, but the evidence warns against that. Tyrannosaurs clearly hunted, yet they also scavenged when the chance arose, which is exactly what a sensible large carnivore does. Raptors were agile and fierce, yet the famous idea of coordinated packs like wolves is hard to prove. Juvenile tyrannosaurs may have hunted in groups, but the bones are quiet on social structure most of the time. What we can say with confidence is that senses were keen. The inner ear anatomy of tyrannosaurs suggests good head stability and sound detection. The nose region is large and full of turbinates for scent. Eyes face forward enough to give depth perception. Add to this a brain that was large for a reptile, and you have an animal that could make decisions on the run. Every predator meets the same problem. Even a small mistake can be fatal when your work involves horns and clubs and stampedes. Skeletons confirm this. Healed fractures are common. Arthritis in joints shows the cost of a lifetime of lunges. Bite marks on faces speak to arguments over carcasses that ended in torn lips and cracked bone. Yet these animals kept going. Bone remodels and thickens around injury. Limps become part of a familiar stride. A tyrannosaur with a tooth abscess that ate through the jaw survived long enough for bone to regrow, which means it fed through pain and winter and came out the other side. By the last chapters of the Cretaceous, the choreography was set. Herds poured down valleys toward fresh growth after storms. Along the edges moved shadows with patient gaits. At night, the small hunters took their turn, eyes reflecting starlight as they worked the margins of water and reed. At dawn, there were tracks in the mud that crossed and overlapped, and sometimes there was a furrow in the sediment where a heavy body fell and was dragged a short distance and then stopped. It is not a sentimental picture. It is simply a working landscape in good order. If you could stand on a bluff in western North America about 66.5 million years ago, you would see a country that feels familiar and alien at the same time. The inland sea that once split the continent has withdrawn like a slow tide and left behind a broad patchwork of river valleys, oxbow lakes, swamps, and pine-studded uplands. The air is warm, the light slightly hazy, and storms roll in most afternoons to drop heavy rain. Dragonflies skim low over backwaters. Turtles bask on rotting logs. On the far bank, something moves through the ferns and reeds with the calm weight of a freight train. A herd of Edmontosaurus rises out of the greenery, skin creasing over thick necks, mouths busy with leaves. Young animals tucked toward the middle where it is safer. A few minutes later, the ground gives a little thump that you feel more than hear. A Tyrannosaurus is there, head level with your chest even from across the river, eyes set forward and steady, every step measured and quiet. The landscape is not a museum diorama. It is a working floodplain, and it is busy. Cottonwood and dawn redwood line the channels. Magnolias and sycamores shade the banks. Ferns and horsetails fill open ground. Flowering plants are now the backbone of the flora, and they shape the soil with roots and the air with pollen. Bees and wasps are common in the warm season. Small mammals slip between roots and make quick harvests of seeds and berries. Crocodilians lurk along quiet reaches where the current slackens. Above the water, Flocks of birds move in fast arcs, and a few larger forms coast on the updrafts over the river valley. The karst on land is rich and local. In the west, across Laramidia, dinosaur communities sort themselves by region and by habitat in a pattern that paleontologists call provincialism. Northern valleys hold their own blends of horned and duck-billed species. Southern basins host cousins with different frills and different crests. You can walk rock layers in Alberta and count several large plant-eaters living side by side. Go to New Mexico and the mix changes and the headgear changes with it. The reason sits in the shape of the land. Mountain building to the west raises ranges that feed rivers with sediment and rain. The inland sea to the east regulates humidity and carves long belts of wet ground. The result is a chain of distinct neighborhoods that lie only a few hundred kilometers apart. Herbivores use this patchwork with ease. Hadrosaurs graze where grasses are still rare, but low herbs and shrubs are plentiful. Their dental batteries grind plant matter into paste, and they keep at it for much of the day. Triceratops trims woody stems and browses on shrubs, the jaw muscles anchored on a neck frill that is as much engine mount as display. Ankylosaurs rumble along the thicket edge. Their broad backs are tiled with bone, and their tail clubs sway with the slow rhythm of a pendulum. Pachycephalosaurs cross the open glades in twos and threes, heads carried low, domes polished by use and age. The young of all these animals move in the shelter of adults or near stands of trees that give fast cover. Predator and prey both understand the geometry of the valley. The record of daily life lies scattered and quiet. Tracks crisscross sandbars and then vanish under a thin sheet of silt. Chewed twigs with fine parallel grooves mark where a hadrosaur worked a branch like a file. Coprolites from plant-eaters carry bits of leaves and seeds, sometimes even fragments of soft fruit stones. A triceratops horn core shows a crack that healed with thickened bone, which means the animal lived on for months after a fight or a stumble. A tyrannosaur toe bone carries a gouge that matches a horn point, and the edges of the wound have rounded with time. These are small notes from long lives, and they show that the last Cretaceous ecosystems were not failing. They were running hard. The water itself is crowded. Rivers are full of gars, bowfins, sturgeons, and a fine drift of smaller fish. Freshwater mussels sit half buried at the margins. In some reaches, you can still taste the influence of the sea because the western interior seaway has not gone entirely. Farther south and east, it still covers broad provinces. Its margins are shallows where sharks hunt and where mosasaurs surge among schools of fish that glitter like a disturbed mirror. Ammonites ride the upper water in coiled shells marked with intricate sutures. Their population numbers pulse with changes in sea level and temperature, but they remain a common sight offshore. Pelicans and early relatives of gulls work the edges and rest on sand spits that appear and vanish with each storm. Over on the far side of the world, in the basins of Mongolia and northern China, the light is harsher, the soil's paler, and the wind has more room to reach you. Here the late Cretaceous carries broad fans of sediment out from low ranges and lays them down as sheets of sand and silt. Seasonal streams cut channels in wet months and leave braided bars to bake in the Sunday. On those bars you find the bones of protoceratops by the dozen, individuals of all ages, sometimes crouched in hollows, sometimes in pairs that look like they were sparring when the dune fell. Saurolophus moves across the flats in lines that have the tidy spacing of a practiced herd. Tarbosaurus hunts where the dust devils collapse and leave the air still. Velociraptor keeps to the edges and looks for young or for anything caught in a washout. Oviraptorids brood nests in rings and spread feathered arms in a circle above their eggs. Storms here are dry more often than wet. When rain finally comes, it comes as a wall. That is why so many animals lie where they fell with little disturbance, as if a shutter flicked across the sun and stopped time. South America has its own late Cretaceous rhythm. Patagonia carries wide floodplains with low bluffs and wind that moves low grass in the same direction for hours. Titanosaurs still graze here, though the giants of earlier times are less common this late in the period. Saltosaurus moves in groups across a mosaic of forest patches and open ground. Armor plates dot its skin and give a fine rasp to the touch. Abelisaurid predators with thick skulls and short arms track these herds. The arms look comically small to a modern eye, but the rest of the animal is all business. The face is heavy-boned and can take a blow. The mouth is full of serrated teeth that slice rather than crush. When river levels drop and expose new bars, you find eggs by the dozens set in shallow pits, the shells thin and porous, a sign that they were covered with plant matter to warm them as they developed. High latitudes complicate the picture in a way that feels surprising until you remember how warm the world island. In Alaska, and in what is now northern Alberta, dinosaur trackways cross beds that were laid down near the shore of the inland sea. The tracks continue through layers that represent winter months. Growth rings in bones from these regions tell of a seasonal pace, rapid growth in summer, slower growth in winter. The story fits with a life spent in place rather than a long migration. These animals likely stayed through the dark season and fed on evergreen twigs and stored food in floodplain hollows. In Australia, when it was still linked to Antarctica, small herbivores with large eyes lived in forests that saw long twilight. Their limb bones show growth that did not stop, which means they kept moving and feeding through months of low light. Cold was not the barrier we might assume, because the global climate was still warm enough to keep winters mild by our standards. Fires run through the story as well. Charcoal is common in these rocks. Lightning strikes dry forests and sets leaf litter alight. Stands of conifers go with a rush. Ferns colonize the ash beds within weeks. Flowering shrubs follow the ferns. By the next wet season, the ground is green again. If you look closely at soils in the fossil record, you can see this cycle. There is a dark band from a burn. Above it, a light band of clay where ferns grew. Above that, a thicker soil where roots from larger plants have gone down into the profile. Herbivores take advantage of the flush of growth after a burn. Predators drift to the same places because the prey is there. The system does not resist disturbance, it uses it. While all this plays out, the planet rumbles in the distance. In what will one day be India, flood basalts begin to pour from long fissures. Layer upon layer of lava builds a stepped landscape that modern geologists call the Deccan Traps. The eruptions add gases to the air and leave a signature in carbon and sulfur records. The climate can wobble when pulses are strong. Rain patterns shift a little. Sea level edges up or down. Local ecosystems notice and adjust. But there is no sign in the rocks of a world that is losing its grip. The bone beds are full. The pollen record is busy. Trackways are fresh. If you lived in this time, you would not sense an ending. You would sense a full season with enough food and a few more storms to come. The pace of life is normal. Herds follow chutes along the river after a flood. Triceratops, cows, steer calves between themselves and the thicket. A tyrannosaur walks a ridge at dawn and looks into the fog sitting in the low ground. A flock of birds rattles up from a branch and settles again when the threat has passed. On the far shore, a small mammal noses under a mat of leaves and finds a cache of seeds that a hadrosaur dropped last week. Farther out over the inland sea, ammonites drift just below the surface, while a mosasaur rolls to swallow a fish that turned too slowly. The day warms. The air smells of water and resin. There is not a hint that anything is about to change. When people first tried to explain the disappearance of dinosaurs, a tidy story was hard to resist. Perhaps they were already failing. Perhaps climate had cooled and food had thinned and the old reptiles had simply dwindled away. The rocks do not tell that story. The youngest Cretaceous layers from North America, Asia, and South America show busy floodplains, crowded seas, and a constant traffic of footprints. Bones are common right up to a razor-thin boundary, and above that line the large dinosaurs are gone. The pattern looks like a curtain drop rather than a slow dimming. That sharp boundary is easy to find if you know what to look for. In many places it is no thicker than a finger. It sits between the last dinosaur-rich sediments of the Cretaceous and the first Paleogene clays that hold a very different cast. The boundary clay carries a cargo of extraterrestrial metal. Iridium is scarce in Earth's crust, but relatively abundant in meteorites. At the line, the iridium spikes far above background. Mixed with it are mineral grains that have been shocked by intense pressure, and tiny spherules that formed when molten spray cooled in the air and fell back as glassy beads. In short, the layer reads like a forensic lab report. A large object struck the planet and left a dusting of fallout that settled across the world. The crater lies mostly under the shallow seas off the Yucatan Peninsula. Its buried rim outlines a circle nearly 200 kilometers across. Drill cores taken from the structure show broken and melted rock and a ring of uplifted crust that rose like the edge of a splash. The timing is precise. Radiometric clocks in minerals that were reset by the heat match the age of the boundary layer. Around the Gulf of Mexico, tsunami deposits sit just below the iridium-rich clay. They are full of ripped-up coastal material, broken shells, and boulders tossed inland and back again by waves that would have towered over any building. Farther afield, as in the American interior, you can find thin layers where tiny glass spherules settled out of the sky into lakes and rivers. One site in North Dakota records a remarkable sequence. There, the last Cretaceous river channel holds fish packed in tangled layers, gills clogged with spherules that fell into the water within the hour after impact. Trees lie blown down in a common direction. The sediment shows that standing water suddenly surged and ran back, which fits the idea of a long seiche wave sloshing through inland basins after distant oceans had been kicked like a tub. This is not the only record of chaos, but it is among the clearest snapshots of the first day. It tells us that the immediate effects were global in reach and violent in detail. The short-term shock would have killed many creatures outright. The years that followed brought a quieter and more thorough trouble. Dust, sulfate aerosols, and soot from worldwide fires rose high into the stratosphere and hung there. Sunlight dimmed. Photosynthesis stalled over land and sea. Climate models and geochemical records point to a sharp cooling that lasted long enough to starve food webs. In the ocean, the plankton base faltered, and everything above it felt the loss. On land, the first to suffer were the large herbivores and the predators that depended on them. Animals with low metabolisms and slow growth could not bridge the gap. Plants that relied on long growing seasons lost ground to hardy pioneers that spread quickly after fire and frost. The selectivity of survival leaves clues about what mattered. No large land animal made it through. The winners were small and adaptable and able to eat many things. Creatures that could hide in burrows or water did better. Diets that could switch to seeds, detritus, roots, or carrion were an advantage. In plant communities, there is a brief but telling fern spike in many places. Ferns are early colonists after disturbance. They cover bare ground while forests wait for better seasons. In the rock record, this looks like a sudden surge of fern spores right above the boundary line. It is a signature of burned and cleared landscapes on a global scale. What about the long volcanic episode in what is now India? The Deccan eruptions began before the impact and continued after it. They pumped gases into the air and loaded the climate system with additional stress. In some intervals, the eruptions rose to dramatic peaks. It would be comforting to assign the extinction to a single cause, but the likely truth is more layered. The impact drove the mass extinction. Volcanism may have nudged climate and acidity and made ecosystems more fragile in the years around the event. And in the aftermath, it may have complicated recovery in some regions. The key point is timing. The most abrupt biological losses line up with the boundary clay and the fallout markers, not with earlier pulses of lava. Were dinosaurs already fading in the millions of years before the end? Several lines of evidence argue that they were not. Diversity counts corrected for gaps in sampling remain high in the final Cretaceous formations of western North America. In Asia, the youngest dune and floodplain deposits still yield varied communities with hadrosaurs, horned forms, ankylosaurs, and multiple predators. Bone histology shows healthy growth in late individuals and does not point to a long decline. Plant records do not show a sustained collapse before the boundary. In short, the lights were on. The day was normal. The extinction looks sudden because it was. The very last dinosaur moments are as ordinary as any others in the record. You can pick up a hadrosaur jaw with fresh toothwear in the highest dinosaur-bearing layer and then walk a few steps upward into a barren clay. You can map trackways that cross a wet bar and end under a film of ash and spherules. None of these signs carry any warning. The animals were living their usual lives until the planet changed beneath their feet and above their heads. This perspective matters because it changes the lesson. The end did not come because the dinosaurs failed to keep up in a slow race. It came because a rare and violent event made the rules irrelevant for a time. In that interval, small size, flexible diets, and sheltering habits were tickets to the future. Large bodies, slow reproduction, and dependence on abundant forage became liabilities. The best adapted animals for a full and sunny world were the least suited for a dark and hungry one. When the sun returned and plants spread again, the survivors began to write a new chapter on a quieter stage. Picture the moment just before it happens. It is a clear morning somewhere, on the edge of a warm sea. Waves fold over a sandbar. Shorebirds lift and resettle. A hadrosaur wades belly deep where a river meets the coast and noses into reeds for tender shoots. Far out over the water, a bright point grows in the sky. It is silent at first, then it draws a faint line that thickens into a white smear. No one looks up for long, because there is nothing in any memory that calls for fear of a star that falls in daylight. The object is about the size of a city. It is moving faster than a rifle bullet and carries more energy than all the volcanoes on Earth in a busy century. It is a remnant of the early solar system that has wandered into our path at exactly the wrong time. It meets the atmosphere at a shallow angle over the Caribbean and compresses the air in front of it into a white-hot piston. In the last seconds, it is no longer a single stone. The pressure and heat shatter it into pieces that still behave like one body because the speed is so great. A skin of vaporized rock forms along the front. Then the world goes white. The center of the blast is the shallow sea off the Yucatan Peninsula. Water flashes to steam. Limestone and bedrock boil and fly. A cavity opens in the crust that is dozens of kilometers deep. A hole so large that it cannot stay a hole for more than a breath. Rock flows like thick syrup. The walls slump inward. The floor rebounds upward. A ring lifts where the crust springs back like a bell. All of this happens in minutes. If you could watch from a safe distance, which does not exist, you would see the sea pulled aside and then thrown back in walls of water that race outward in every direction. The shock wave leaves the crater and runs through the planet. It is so strong that it rattles faults far away. Coastal shelves crumble and slough off into deep water. On land, cliffs shed faces in sheets. In the Gulf of Mexico, the very shape of the bottom shifts. Within half an hour, the first water returns as a wave that climbs the new crater rim and falls in, then rebounds and races out again, piling into the second wave and the third as a train of giants that cross the basin. When these waves reach far shores, they arrive as rushing walls that pick up forests and roll them into mats, then grind towns of trees into slurries that surge inland and then drain back, loaded with the detritus of a continent. Air brings its own disasters. Debris is thrown high past the atmosphere and falls back over the next hour as beads of glass and ash. These spherules begin to glow as they descend because they re-enter fast and heat the air in front of them. The sky becomes an oven roof. The ground feels the heat as a steady radiance that can set dry brush alight. In places where forest floors hold weeks of litter, flame runs from leaf to leaf and then jumps to crowns. Animals that cannot find shelter in water or in burrows are caught by a heat that arrives without a wind. The fire line is not a single moving front. It is many small fronts that rise together across a continent while the sky still rains glass. There is a sudden storm of stone near the crater that does not care about size. Fist-sized chunks fall like hail. Blocks big as carts come down on the next line from shore. Even far away, where the only rain is sand-fine ash, the fall is heavy enough to load roofs of nests and break shrubs. Lakes and rivers receive a snow of spherules that melt into the surface and stick, a glass confetti that later sifts into quiet corners. In some inland basins, the water heaves in long, slow sloshes that push over banks and drag back again, not in a single wall, but in repeated pulses that last the rest of the day. The sound takes time to arrive. Near the impact, sound is not a thing you hear. It is a thing that crushes your chest and knocks you down. Hundreds of kilometers away, it rolls over ridges as a distant thunder that keeps returning. The pressure wave breaks tree trunks where they stand and strips needles and leaves from anything that does not fall. Birds rise as flocks and are flung from the air. The first blasts push outward. The later ones come back as echoes that have crossed oceans and return altered and delayed. Under the sea, the carnage is different, but no less complete. The first pulse of heat kills plankton across broad surfaces and boils schools of fish close to shore. Then the water changes direction and begins to move. Entire shoals lift and pass like clouds under a sun that can no longer be seen. Mosasaurs ride the pressure slopes in one moment and meet a reef where there was open water the next. Sediments that were safe in layers are torn free and move as underwater avalanches that race down slopes and spill out across the abyss in fans. When the motion lessens, the water is full of fine grains and shocked minerals and charcoal. Dust rises into the stratosphere in quantities that are hard to imagine. The impact vaporizes rock that contains sulfur and carbonate. The sulfur leaves the sea as gas and returns as droplets that reflect sunlight. The carbon dioxide will matter later, but not yet. First comes a dimming that begins within hours near the equator and spreads outward as winds carry the load. Before that dimming takes hold, the air fills with nitric fumes made by the shock of the blast. These mix with water and fall as acid rain that stings eyes and skin and pulls nutrients from the soil. The first showers smell like an electric storm. Later ones smell like a wet hearth. The crater itself is not done. The sea rushes back and forth across its rim through the day. Each surge moves hills of new sediment and heaps ripped up blocks into ridges. Rafts of trees that were forests in the morning now turn in slow gyres in bays. Dead animals collect where the water backs into oxbows and has no easy path back to the main flow. Shorelines on the far side of the Gulf carry lines of debris high on bluffs that never saw spray before. When the waves finally subside, they leave a braided memory of the day in layers of sand and rubble that will harden into a page any geologist can read. At the scale of minutes and hours, the event reads like a cascade of simple physics. A body in motion meets a planet. Kinetic energy becomes heat and shock. Pressure becomes wind and water walls. Shattered rock becomes glass rain and falling fire. Each step follows the last with a terrible logic. At the scale of lives, the picture is worse. Nests burn. Herds scatter and do not find each other again. Animals that survived the first hour stumble through a dusk that begins too early and carries a red glow. The map of safe places has changed and keeps changing as embers land and gusts rise. Night falls on a planet that has been hammered flat in places and scorched in others. Smoke rises in lanes that stretch from horizon to horizon and drift into belts around the world. The sea keeps moving even when the wind dies. The ground keeps shaking in aftershocks that rattle loose stones from ledges and send thin fans of dust down fresh scarps. The stars are gone. A faint copper light hangs where the sun should be. Somewhere far from the crater, a small bird settles on a branch and tucks its head beneath a wing while ash patters on the leaves. It sleeps because it must. It sleeps into a morning that will not look like a morning at all. The day after, the impact did not arrive with a sunrise. The sky turned the color of old copper and stayed there. Fine dust, glassy beads, and soot from burning continents rode the winds into the high atmosphere and refused to come down. Sunlight weakened to a dim glow that could not drive photosynthesis. Plants paused as if holding their breath. In the oceans, the same brake was thrown on the tiny drifters that feed everything else. Food chains are ladders, and every rung rests on the one below. When the bottom rungs give way, the collapse climbs upward quickly. Temperatures fell. The stratosphere filled with sulfur droplets that bounced light back into space and turned the planet cool despite the fires. Lakes skinned with ice at latitudes that rarely freeze. In coastal waters, tropical corals bleached and then vanished. On land, forests that did not burn browned and shed leaves in a season that did not end. Where the ash settled thickest, whole hillsides wore a muffling coat that held moisture and smothered shoots. The air smelled of damp charcoal and sour rain. Storms washed nitrates from the sky and made the soils briefly rich and hostile at the same time. The first weeks were the killing time for large bodies. Great herbivores needed daily tonnage of greens that no longer existed. Predators that lived by taking those herbivores met the same wall a little later. Starvation leaves marks you can read long after the flesh goes. Bone tissue stops laying tidy lines and switches to ragged patterns that speak of stress. The fossil record around the world shows a sharp ceiling for body size right above the boundary clay. Nothing heavy makes it through on land. The winners are small, hidden, and not very picky about dinner. Ferns spread. Their spores do not wait for a forest to return. They settle on bare ground and grow wherever moisture lingers. In many sections, the first Paleogene layer above the iridium-rich clay is thick with fern spores. It is a green flag planted in blackened soil. Fungi bloom as well. A spike of fungal remains in some cores points to a world rich in dead wood and damp leaf beds. The living cover pulls back, and the recyclers pour in. That is the first step in any recovery, even one that will take years to gain speed. Fresh water becomes a refuge. Streams still carry washed-in seeds and drowned insects. Ponds hold turtles, lungfish, and amphibians that can sit tight in mud or under banks. Crocodilians fare better than most because they can wait and because their young grow on diets that do not demand abundance. In burrows, small mammals ride out the worst on caches of roots and seeds. Some gnaw their way through a season of gloom to another season only slightly brighter than the one before. It is not a comfortable existence, but comfort is not the currency of survival in a world like this. Sea life faces a different sort of siege. Plankton die-offs starve ammonites and many bivalves. Foraminifera, the tiny shell builders that mark ocean time like grains in an hourglass, crash and then reappear as new forms. Acidified surface waters dissolve carbonate shells more easily and push the depth at which shells survive upward. This shoaling of the compensation level squeezes habitats. Large marine reptiles vanish completely. Sharks and teleost fishes endure but reshuffle their ranks. Along continental margins, turbid layers settle out after each storm and leave thin alternations of light ash and dark silt that look like the heartbeat of a tired patient. Air quality is not only dim but harsh. Nitrogen oxides made by the blast and the fires strip ozone and leave more ultraviolet to reach the ground once the dust thins. That adds insult to injury for seedlings and surface dwellers. In some lake records, pollen falls almost to nothing and then returns with a new cast. Hardy pioneers move first, followed by shrubs, and only later do trees take hold. The pattern is not uniform. Valleys with spring-fed water come back sooner than dry uplands. Coasts sheltered by headlands nurse patches of green while open shores stay bare. Even in a global disaster, geography keeps its say. Months turn into a handful of years. The dust veils thin and light returns in fits and starts. Winters remain sharp for a while because the stratospheric haze lingers longer than the soot. Summers brighten, then dim again as different layers of debris descend. Each brief recovery builds a little plant mass and then sees it pared back by frost or a late storm. The animals that make it through this seesaw are those that can breed quickly, hide often, and eat whatever they find. Teeth suited for a single food become liabilities. Beaks and jaws that can manage seeds, carrion, and tough shoots become tickets to the next season. Whole regions change their character. In western North America, the river belts that once hosted mixed herds settle into simpler communities of small browsers, wading birds, turtles, and crocodilians. In Europe, island chains with thin soils lose much of their tree cover and rebuild from shrubs upward. In Asia, basins that were once crossed by herds of duckbills and horned dinosaurs now see birds and small mammals claim the banks. The absence of big feet and heavy bellies lets soils develop without constant trampling. The soundscape changes most of all. The deep thud of giant steps and the hollow coughs of large predators give way to insect hiss, frog calls, and the clatter of seed-eaters. The speed of recovery is uneven but impressive where conditions are kind. In the ocean, plankton rise first because their generations are short. Once they return, fish numbers follow. On land, ferns carpet ground within months in humid belts. Grasses are minor players at this time, yet hardy flowering shrubs prove quick settlers along streams. Birds that eat seeds and insects move fast into these green corridors. Mammals that had been night workers try daylight under the softer Sunday life never stops. It merely shrinks and simplifies, then reaches forward again when the energy returns. None of this erases the scale of loss. Ammonites, which had survived other crises, do not return. Pterosaurs vanish entirely. The immense dinosaur line that ruled the ground for more than 160 million years ends in silence except for one narrow branch that we now call birds. That survival is the hinge. It means the story of dinosaurs does not end. It changes size and tempo. Feathers carry the lineage onward through sparrows, herons, and hawks. The old ground thunder becomes wing beats. By the time a few years have passed, mornings finally look like mornings again. The sun comes up clean more often than not. Shoots push through ash. Soil profiles begin to show new roots. Rivers run their old paths. The planet has moved from impact winter into an early Paleogene that will warm under a different mix of gases. The stage is ready for the quieter revolution to come, when small survivors grow into the rulers of a new era. Morning returned slowly, but it did return. Once the ash thinned and the sun found the ground again, life began to rebuild in ways that would have looked humble at first glance. The first Paleogene landscapes were quiet places of ferns, low shrubs, and young rivers that ran brown after every storm. Where the inland sea in North America had once spread, broad floodplains settled under cottonwood and willow. Across Europe, islands that had been scoured by wind and ash were patched with thickets. In Asia, basins that only recently had held herds of horned and duck-billed dinosaurs now held birds and small mammals along the reed beds. The world felt scaled down. That was not a weakness, it was a strategy. The earliest chapters after the boundary are written best in river muds from western North America. In the Denver Basin and the Hell Creek to Fort Union succession, you can walk from the last Cretaceous layers into beds where the first Paleogene mammals appear in earnest. They are not impressive in size. Most could sit in your hand. They are impressive in variety. In a few 100,000 years, the roster grows from simple insect eaters and seed nibblers into communities with early meat eaters, fruit specialists, and root diggers. Paleontologists give these intervals homey names like Puercan and Torregonian, and within those slices, you can watch tooth shapes diversify the way tools diversify in a busy kitchen. Shearing edges for meat, rounded cusps for fruit, tall crests for grinding leaves. When the menu broadens, mouths follow. Birds answer the same invitation. The branch that survived the impact expands with speed. In the southern polar regions, there is a bird named Vegavis, known from Antarctica, that carries features close to modern waterfowl. In New Zealand, a little later, stout penguins such as Waimanu dive after fish in seas that are still unusually warm. In the northern hemisphere, lakes that will later form the Green River shales host flocks of shorebirds, perching forms, and early swifts that dry their wings on snags. The air fills again, this time with smaller bodies and quicker beats. The great aerial reptiles are gone, but the sky is far from empty. The land warms in fits and starts, then takes a dramatic step during the Paleocene-Eocene thermal maximum, an ungainly name for a sudden spike in temperature about 56 million years ago. Carbon flooded the atmosphere and oceans. Winters softened even at high latitudes. Palms grew in Wyoming. In the Bighorn Basin, red and ochre bands of clay-mark floodplains where forests thickened, and the fossil record shows that many mammals responded by getting smaller. Dwarfing happens when food webs are stressed by heat and drought, and when plants change their chemistry. Horses that were already no larger than a medium dog became smaller still for a time. When the climate relaxed, bodies grew again. The lesson is a simple one, repeated across ages. Size is not a ladder you climb once. It is a dial that turns with the weather. Even before that warm pulse, the main branches of modern mammals had begun to spread. The placentals, which bring young to a later stage before birth, diversify into lines that we recognize as hoofed runners, early primates, carnivores, and odd generalists that try many ways of living. The marsupials, which raise young in pouches, take a strong hold in South America and later make their great crossing to Australia, where they will write most of the local story. The monotremes, the living echo of deep time, keep a toehold with egg-laying platypuses and echidnas in the southern lands. The pattern is geographic as much as it is biological. With the end of the dinosaurs, continents become both classrooms and fences again, and each teaches its students different tricks. South America is the best example of this continental education. Cut off from the north for a long stretch, it grows its own caste. The ground shakes to the steps of terror birds, large flightless hunters with heavy skulls and hooked beaks that sprint across savannas and river flats. The herbivores answering to them are not horses and antelope at first, but strange hoofed mammals with body plans you would sketch only after a long day. Lithe runners with 4 toes, stocky grazers with odd teeth, and sloth relatives that will later climb trees the way sailors climb rigging. Far to the north, on the other side of the Central American seaway that still exists, North America develops a different set, with early perissodactyls that will become horses and rhinos, and artiodactyls that will become deer and cattlekin. These paths will not meet until land rises between the continents much later, and when they do, the exchange is dramatic, but that is a later scene. Europe and Western Asia carry their own answers. In Germany, the oil shales at Messel preserve a lake community from the early Eocene in such detail that feathers, fur, and even stomach contents survive. Bats sleep in the record there as full-grown flyers, which tells us that the air was already complicated by the time those lakes were silting in. Primates with grasping hands move through the canopy and leave delicate skeletons in the mud. On the water, crocodilians drift between mats of floating plants, and turtles bask in morning light that arrives through warm mist. If you want to see how complete recovery can be in a warm age, Messel is a postcard. Asia sends a different card from the shore of an ancient Tethys. In Pakistan, fossil beds that formed along coastal rivers hold a sequence of early whales. The first look like wolves with long tails and ears still tuned for land. These are the Pachycetids, foot in the water and head still in the forest. A little later comes Ambulocetus, with limbs that have become oars and a body that moves through water with a crocodile roll. Then come forms with nostrils sliding back toward the eyes and tails that do more work than legs. By the Middle Eocene, fully aquatic whales swim in oceans their land cousins can no longer reach. It is one of the finest evolutionary stories on the planet, and it starts in the first stretch after the dinosaurs. If you trace the ground instead of the water, the hoofed lines offer their own steady tail. Early horses skip through Eocene forests on small feet, with 4 toes in front and 3 behind. Their teeth are suited to soft leaves and fruit. As climates dried and open woodlands widened, grasses began to appear more often along floodplains. Grass carries silica in its blades like fine grit, which wears teeth. Horses answer across millions of years by evolving higher-crowned molars and fewer toes for running on firmer ground. The artiodactyls split into deerkin with antlers and bovids with horns. Camels and pigs and hippos leave their marks along rivers and sands. You can follow these changes within layered rocks the way you can follow chapters in a long book. Each page is a jaw, a limb bone, a footprint. Birds make parallel moves. In the early Paleogene, large land birds appear on several continents. In Europe there is Gastornis, a heavy-bodied giant with a massive beak that once was cast as a terror bird but now seems to have used that beak mostly on tough plant matter. In South America, the true terror birds take up the apex role in some regions, and they hold it until cats and dogs and bears arrive from the north much later. In the seas, penguins flourish in the southern hemisphere where cool currents meet warm shelves. Their bones stack in cliffs by the hundreds of thousands, a record of a life spent flying through water. Through all this, small things carry the future forward. Rodents spread with a suite of tricks that include ever-growing incisors and a talent for gnawing that would make a carpenter curious. Insect-eating mammals split and specialize, some becoming hedgehogs with spines, others becoming shrews with metabolisms so quick they must feed every few hours. Bats perfect their radar and fill the night sky with flights that leave barely a trace in the rock record. And in the trees, early primates refine grasping hands, forward-facing eyes, and the sort of curiosity that sends them out along branches where fruit hangs. These are not our ancestors directly in most cases, but they sketch the outlines of the primate plan that will later include apes and humans. The Paleogene is not a single smooth rise. Seas pulse in and out of basins. Mountain ranges lift and shed their tops to rivers that carry fresh sediments across plains. Climates trend warm, then cool again. When the Antarctic separates from South America and a circumpolar current begins, the planet tips toward a cooler mode. Forest belts thin in some mid-latitudes and grasslands expand. That shift will reshape the mammal world in the Neogene. But the foundation is already set. The age of mammals, as we like to call it, is not only about big bodies. It is about speed of generation, flexible diets, parental care, and a knack for exploring new niches when doors open. What matters most in this first act after the dinosaurs is how quickly complexity returns. River corridors that once echoed with the footfalls of giant reptiles now rustle with mammals, buzz with insects, and ring with the calls of birds. Lakes that once held ammonites in distant seas now hold schools of bony fish and turtles that surface with a small puff. On coasts, the first true whales chase shoals where reptilian hunters once rolled. In forests, primates test branches that had not carried anything quite like them before. The planet did not forget how to be busy. It simply changed the cast. Stand outside on a spring morning and listen. The trills, chirps, hoots, and whistles are the living chorus of dinosaurs. That sounds like a joke until you follow the bones and lungs and eggs back through time. Birds are dinosaurs by strict descent. They share the wishbone that braces the chest. They breathe with a flow-through system of air sacs that turns their bodies into bellows. They lay hard-shelled eggs, and many brood them with the same spread-armed posture that small feathered theropods used in the Cretaceous. Some modern birds even carry a temporary tissue inside the thigh bones, called medullary bone, when they lay eggs. The same sort of calcium store that paleontologists have found inside the bones of a giant predator from long ago. Line up a falcon skull and the skull of a small Cretaceous hunter, and the family resemblance is hard to miss. The legacy lives in movement as well as in bones. Watch a heron lift from a marsh. The neck pulls into an S shape, the legs trail, the wings beat in deep strokes. Those movements were rehearsed in forests of the early Cretaceous by animals about the size of crows that scrambled up trunks and fluttered between branches. On the ground, modern birds run and pivot with the same balance tricks that their ancestors used when they chased lizards under ferns. Quill knobs on the forearm of a velociraptor tell of strong feathers. The same little bumps line the arm bones of many living birds. Even the smallest details persist across oceans of time. If you prefer your dinosaurs large, their legacy runs through stone instead of air. The places they lived and died make up a world atlas of deep time. There is the Morrison country of the American West, where river sands piled up 150 million years ago and now hold bone beds of long necks and their hunters. There are the flaming cliffs of the Gobi, where wind and storm buried nests and brooding parents in dunes that still hold their secrets. There are the fine-grained lake beds of Liaoning that deliver feathers as clear as leaf veins. There are the red badlands of Patagonia, where titans left their eggs by the thousands in low mounds. There is the Hell Creek country, where the last evening of the Cretaceous lies a short walk below the first morning of the Paleogene. These places have turned fossils into common nouns and given us a map for a world that would otherwise be blank. The story of how we uncovered this map is part of the legacy. Early discoveries were accidents on quarry floors and in coal seams. Then came the age of hungry competition, when rival collectors raced across the American frontier in railway cars full of picks and plaster. The Bone Wars between Othniel Charles Marsh and Edward Drinker Cope produced more heat than light at times, but they also filled museums with the first full skeletons of the giants. Later, expeditions crossed deserts in Mongolia and walked out of the Gobi with the first dinosaur eggs and delicate embryos curled inside. In recent decades, teams working with local communities in China, Argentina, and Africa have turned badlands and farms into scientific windows. The field has grown from trophy hunting to careful ecosystem work. Fossils are no longer just spectacular bones in halls. They are data points for climate and behavior and growth, stitched together by radiometric dates, stable isotope chemistry, and the microscopic study of bone tissue. Dinosaurs have taught us how to read time. Before their bones were known, the scale of Earth history felt vague. With them, we learned to think in tens of millions of years. A growth ring in a sauropod leg tells the story of wet and dry seasons in a Jurassic forest. The texture of a tooth wears like a diary of a diet. The mix of carbon and oxygen in a shell records the temperature of a sea that existed before mammals were more than furtive night things. A single ash bed sandwiched between floodplain muds can be dated to the year in a range of uncertainty so small that it feels like precision in a universe of patience. The animals became clocks. They have also taught us caution about absolutes. For a century, we drew dinosaurs as cold and sluggish because they were reptiles. Then came the evidence for fast growth, high oxygen needs, and bird-like lungs. We imagined scaly hides everywhere until Liaoning showed coats of filaments and veined feathers on many branches of the family. We thought of them as separate from modern life until bone chemistry and nest behavior and the anatomy of the chest spelled out a clear line to birds. The picture did not flip in a day, it sharpened with each new find. The lesson is useful outside paleontology. The more you learn, the more the world refuses to stay simple. They left more than facts. They left a permanent mark on our imagination. Every child who looks up into the ribs of a mounted long neck and feels small but happy is a beneficiary. Museums built around these skeletons are cathedrals of curiosity. They invite questions about scale and change and the strange speed of time. Books and films have taken liberties, as they will, but the sense of wonder they spark has sent a surprising number of people to careers in science. It is hard to think of another group of extinct animals that has served as a better gateway to thinking carefully about the natural world. The living legacy reaches our dinner table and our windowsill. Chickens are small dinosaurs that have traded claws for coop life, but kept the same basic skeleton. Pigeons, hawks, and hummingbirds are cousins of Tyrannosaurus multiplied into more than 10,000 species. They navigate by stars and smell, rain, and remember food caches across seasons. They are what a dinosaur lineage looks like when given a new set of opportunities and a sky that needs filling. When we study how birds see and migrate and sing, we are conducting experiments on an ancient theme. There is a sobering inheritance too. The end of the Cretaceous taught us that the planet can change suddenly and that size and dominance offer little protection from bad luck on a cosmic scale. The iridium line is a reminder that accidents can redraw the tree of life in a geological instant. We learned from this that it matters to track the rocks that cross Earth's orbit. We learned that ecosystems with many small and flexible players rebound faster than ecosystems built of few giants. When we talk about resilience and recovery today, much of the language and logic comes from reading very old catastrophes and very old repairs. Finally, the legacy is humility. Dinosaurs ruled for a span of time that makes our entire recorded history look like a minute before midnight. They rose from small beginnings after a crisis, filled the planet with forms that still astonish us, and were gone in a run of bad years that followed a single day. Their story tells us that success is real, but never permanent, that worlds can thrive and then tilt, and that the survivors often look modest at first. It also tells us that life is good at starting over and good at finding new ways to be beautiful. Every time you see a bird lift from a wire and fold into the sky, you are watching that claim made fresh.